Hello and welcome back. Today I am very excited to show you version 2 of the binary databases and the new format for MBDs. In addition, I'll also go over the importing and exporting interfaces as well as some implementations. Since it has been quite some time since the persistence code was touched, it's probably best to give a brief recap of how the old system worked, then show how it has evolved into the new system. Previously, we had something like this. A manifest data description, or MDD file, would contain various data about a scene or collection of scenes. After all MDDs are loaded, they are ran through a series of conversions that ultimately export into a binary format. In this format, you have a table header that says how many entries and then the entries themselves. These entries are indexed by the position index in the header. The entries were built in a fashion where they had a header themselves that contained member types and values that would be read back in as runtime objects. If you're interested, I've left a link in the video below. However, this first model ultimately has serious flaws, which we will address now. First and foremost, the major flaw with the old design was we had zero control over the actual entries in the database. This made querying the database for a specific entry almost impossible. And even if you could, a database rebuild risks shifting entries out of place. To solve this, we add a table of contents in addition to our table header and payload. Inside the table of contents, we store entry keys. The keys are made of a U64, which is computed from hashing the fixed size entry name. And a quick note, the entry name here is something that would be used in building and tooling, not actually during the game. Finally, we have an entry position which serves two purposes. During building, the entry position stores the size of the actual entry, including dynamic storage. And during export and runtime, the entry position stores the offset in the file where the object data begins. The next change has to do with this table payload. We no longer have binary types that act as an adapter to runtime UDTs, but instead an interface for importing and exporting all runtime types. This allows us to store just the object data directly into the table and avoid this fractal storage design. Before moving on to the importers and exporters, I want to talk about the layout of the database and their entries. In the old system, the entry position was based on the generation index. In the new design, the hash of debug names are sorted from least to greatest, and then at build time, the sorted order of keys and objects are exported. This allows us to avoid doing a linear search across the entire database whenever loading an entry. Instead, it allows us to do a binary search, moving our lookup times from ON to O log of n. Taking a look at the exporters first is quite literally just handling exporting. A database exporter is essentially a wrapper over some type T and then implements some predefined export function to write the object to file. One caveat with the current system is we can only handle strings, vectors, and trivially copyable objects. Nested dynamic storage still needs to be worked out. I'll go ahead and show a couple of exporters now. These are the ones used for game objects and object instances. First up is the game object itself. These would be loaded when an instance is created to get the base data for that object. Here, we first export the object name, then the bitcode about the modules the object interacts with, followed by a specific object interaction for special units, and a flag whether or not the object is an entity or physics object. Then the objects are very simple. We just export their IDs. It's also important to note not all object fields need to be exported. Some fields are able to be generated during runtime. Flipping over now to the importers. There's a little more going on, but we'll look at this virtual construction function first. This is basically a mirror of the export functions. Whatever the export order was, we replicate on the import. For example, game objects export string vector object object, and then import string vector object object. The major pain with this system is still needing to write the importer and exporter, as well as builders that we'll be talking about in the next video, for each UDT you wish to serialize. However, the interface is built to be as frictionless as possible once the boilerplate is written. Minor changes should amount to just changing what is imported and exported, or the order thereof. Taking a look back at the importer interface, we also have two load functions exposed for use. The first will import the entire database into a database builder. This function is used for importing a database back into the build tool to modify or continue working on it. The next function is load entry, and this is used during runtime to find specific entries in their respective binaries and return a new constructed object. While we're here, I'll give a peek at something for the next video as well, but that load entry function in most cases is actually never called directly. An engine module exposes their own load function and calls this load entry function, supplying their own private importer member. However, that is really all for today, pretty short and sweet. I thought this would be a good starting point to begin looking at the inner workings of the architecture I overviewed previously. If we recall, the end goal is to have one main binary file that houses all the various databases, so naturally we'll need a way to get data in and out of there. In the next video, I'll go over the next layer of the game engine with the database builders and the engine modules. Thank you so very much for your time, and I will see you in the next one.